Now in class we observed what happens if you have some liquid in here. Liquids may be this deep here, you invert this, and the liquid has a different depth when it flows down into the narrower tube. Now these tubes are not perfect cylinders because they're not perfectly straight, but they could be straightened out and it wouldn't make a lot of difference. Okay, now we want to solve the mathematics of this situation and gain some really important insights. Okay, now first of all, again, I don't know how this is developed, but nobody seems to understand the word cross-sectional area, even though they had geometry. A cross-sectional area is an area that's perpendicular, that's measured in a plane that's perpendicular to the altitude. So that if we have the altitude of this cylinder, and let's assume that we've straightened it out, if we have the altitude of this cylinder, the cross-section is the shape we get when we cut the thing perpendicular to that altitude. If the altitude is vertical, then that means we're cutting the object with a horizontal plane. If the object is horizontal, then the altitude goes in this direction, perpendicular to that is a vertical plane. No matter how we rotate this or orient it in space, the perpendicular to the altitude is going to be give us the same shape. Okay. Now, if we have constant cross-sectional area in a cylinder or a prism or anything else, we have a constant cross-sectional area, constant area perpendicular to the altitude of a three-dimensional geometric figure. And that's basically cylinders, prisms. Then the volume is going to equal the cross-sectional area multiplied by the altitude. Now, we didn't have time to talk about why that's the case, but that is the case. And in a subsequent video, we should probably address this idea, because without understanding just what volume means, you don't really understand why this should be the case. And I don't think anybody has a very good understanding of what volume means based on the courses that are aimed at passing an SOL. I'm sure there are exceptions. Some teachers will manage to slip that in. I'm sure most would like to. They just can't do it in a test-driven situation. Okay, anyhow, again, cross-sectional areas measured perpendicular to altitude. Here's a picture of a cylinder. If the altitude is this way, then the cross-section is a circle. Cross-section measured perpendicular to the altitude. You cut this cylinder at any point with a plane perpendicular to the altitude, you're going to get a circle, and the circle is going to be uniform. Okay, going to have the same cross-sectional area at every point. So cross-sectional area is a circle. So what's the area of the cross-section? Now, again, I'm a little incredulous, but people weren't able to reliably tell me what the formula is for the area of a circle. We're talking about bright students who've had a geometry course and have actually had to do this on the SOL. So again, I'm thinking that short-term memory, pass the SOL, and then hopefully you'll remember something to apply later, is really what the test-driven curriculum is leading us toward. Again, I don't blame this on teachers. I don't blame it on administrators. The blame goes much higher than that. It's a nationwide problem, a statewide problem in Virginia. Testing is getting better, but it's got a long ways to go. Okay, it's expensive. We don't have the money to do really good testing, and that's one of the constraints, one of the trade-offs in this thing. Okay, well, politics aside, and this is not partisan politics. This is just a political problem that hopefully both sides could get together and solve. Okay, cross-sectional area is pi r squared because the cross-section is a circle. Okay, so cross-section, measured perpendicular altitude, cross-section is a circle, area of a circle is pi r squared, for r is the radius of the circle. Thus, the volume is cross-sectional area times altitude, which is going to be pi r squared times altitude. And altitude is often designated h, so we have the formula pi r squared times h. Now, people can often tell me this formula. They memorize the formula for a cylinder, or they go look it up to solve a problem, and they remember it, at least for the short term. And if you solve enough problems, do enough of this, you probably remember it for the long term. But this formula, I don't like this formula at all. This formula is what you use when people can't understand this and don't know this, that the area of a circle is pi r squared. So the formula can be harmless, but when it distracts from the bigger picture, the bigger idea, I don't like it at all. So this is often written pi r squared times h, which is a formula that's perfectly good for finding the area of a cylinder. This is much better because it finds the area of anything for which you can calculate the cross-sectional area. Okay, well, that aside, we have a picture here now that depicts a bigger cylinder and a smaller cylinder. And the question was, well, if delta y in 1 second, if the change in altitude in 1 second is this distance here, the distance corresponding to the distance between these half circles as they're drawn here, then by how much does the volume change up here? Now, I've drawn the picture. I'm saying if the volume changes this much here, it probably changes about this much here. That should be consistent with your experience in inverting this system. Whether it is or not, we can reason this out. If you have a constant time rate of volume flow, okay, in other words, the same amount of water going into the system every second, and delta y changes by this much every second, and these are supposed to be at equal intervals, then by how much does y change in a second when it gets to this cylinder? People were pretty good with their intuition saying it would be more than it is here. Now, do I have it right? Is this picture any good? Well, I asked people to estimate the ratio of the cross-sectional areas. How much more cross-sectional area do I have here than here? Well, people said twice as much, 3 times as much, based on the idea that this looks to be about, I'm thinking 1/3 of this, because we can do this here, we can do this here. Some people said half, and that was okay, and actually I was kind of I'm glad somebody chose half. Well, okay. If this has half the radius or diameter of this, that is, you're shrinking the cross-sectional diameter of the cylinder down by a factor of 2, then what's going to happen to the depth of it that you need in order to get the same volume? Well, if we have half the cross-sectional area, it's going to have to get twice as deep. Since the volume is the product of cross-sectional area with altitude, if you have half the cross-sectional area, then in order to get the same volume, you need twice as much altitude. If it's 3 times, if the cross-sectional area is 3 times as great here as it is here, then you would need 3 times the altitude to get the same volume. However, this is not a direct indication of the change in the cross-sectional area, because the cross-sectional area depends on the square of the radius. And if you just look at this circle versus this little circle here, it's clear that this circle is a lot more than 2 or even 3 times the area of the little circle. Well, if you square the ratio of the radii, in other words, if this one has 3 times the radius of this one, then you're going to get 9 times the area. If this was twice as the radius of this, or twice the diameter, either way, then squaring the 2, you would get 4 times the area. So in this picture, it looks like we narrow by a factor of about 3, so we have 1/3 the radius, giving us 1/3 squared of the cross-sectional area, which implies 3 squared times the altitude, or 9 times the altitude. So we need that much change in altitude to match this much change in altitude down here. Okay, that's a very important idea. It's very important for understanding proportionalities and the fact that the proportionalities are not always to the first power, something I'll address probably more in a later video. There are insights to be gained just from that example, and why the ratio of the altitude is not 3 to 1, it's got to be 3 squared to 1. Okay, well, we conclude if the ratio of the radii is 3, then water has to move 9 times as fast in the narrower tube. That is, in 1 second, it's got to go 9 times as high as it would down here. So it's got to be moving 9 times as fast in the narrower tube. So if v is the velocity, and that's a lowercase v, not the uppercase v for volume of the fluid, then if you have a volume or a velocity v1 down here and v2 up here, v2 divided by v1 is cross-sectional area 1 divided by cross-sectional area 2. And you ought to do a little bit of deep thinking and think about why that is. Now that's a very important thing in physics and physical chemistry, and very applicable to biological systems. What happens if blood flows from a larger artery into a smaller one, or from a small artery into a capillary? Okay, this applies. It applies in physiology, it applies in chemistry, it applies in physics, it applies in earth science. You know what happens when you got this big chunk of magma and something compresses it and it comes up through this narrow tube. You have lava streaming up into the air. Same principle. So this is very, very important, widely applicable, and this thing is actually called the continuity equation. Very important idea throughout many of the sciences.